don't. Alrighty. You know, I had a thought just today, actually quite recently today. I don't have thoughts very often. So today I will probably just do, since I don't know an answer yet really, and I want you to think about it, I'll do pretty much what we did on Tuesday, which is what I've been doing. But it does occur to me, since I am recording these sessions, and you know, they could be kind of painful, I think, to listen to when you listen to a recording of these, but maybe not that much worse than being here in person. I do kind of wonder if people might prefer, you know, I do one lecture on Tuesday, which is live to half of you and recorded for the other half, and one lecture on Thursday, which is live for half of you and recorded for the other half, versus the same thing, you know, so two different lectures moving through the material as opposed to the same thing each time. So I haven't posed that at all to the other half. I will do that and pose it to everybody, and I'll probably put up a poll and just see what people would prefer, and because it just occurs to me that might be something that would be better for everybody, but it might be worse. I don't know. You're the students, so you'll get to kind of decide what you think would be best. And I'll have to look at, I'll probably leave a space for comments and all that. So it doesn't even necessarily mean majority wins, but I thought it's worth asking the question to try to figure out what might be the best way to handle these. Okay, but with that, yeah, we're going to look at kind of the second half of chapter 2 today, talk about that a little bit. Last week we talked about just really kind of what you're doing in the project with the random simulation and how those experiments work. Today we'll talk more about the normal distribution and you know, kind of how it is we get to use that and some basic calculation stuff with it. Any questions right now on anything? I'll have to go with a no. Okay. So as you know, in the text, we have this thing shoved in there, the central limit theorem, 2.5, and so we'll look at that a bit to start with, and we talk about that a little bit in the project. The idea with the central limit theorem, and to me it's really actually quite an exciting, amazing thing. I don't know if I'll get you that excited about it, but you know, I think it's a really great thing. And so for the central limit theorem, it says that if you want to look at the mean of a sample, okay? So sample means sample means from any distribution. Okay, and this is really the amazing part. Okay, so from any distribution. So for instance, in the last module, or first module, either module 1 or 2, I guess it was module 2, you looked at random numbers from 1 to 9. And random numbers from 1 to 9, they just make sort of a rectangular looking distribution, right? You know, there's a 1/9 chance of getting a 1, 1/9 chance of getting a 7, you know, all of that. So if you look at a histogram or a bar chart, really a bar chart's the better thing there. If you look at a bar chart of those frequencies, you know, what you saw, especially when you took a bigger and bigger sample, it pretty much looked like a rectangle. It just, the bar chart all had about the same heights. Yet, when we took the sample means of those samples and plotted that frequency, all of a sudden it didn't look the same height everywhere. It had a big peak in the middle. It changed, you know, when we looked at the sample means. And what the central limit theorem is saying is that if we look at those sample means from any distribution as n, the sample size, gets large, do you people watch Saturday Night Live? Does anybody watch that anymore? I have no idea if anybody. Yeah. There was I couldn't even tell you what the name of the drug was, but there was some recreational drug way back there in like the 70s, late 70s, that I guess the expression was it made you feel small, made everything else feel big. So, you know, people would get small. I don't know what it was, but maybe I shouldn't even be talking about recreational drugs, but given I don't even know what the name of it was, I probably wasn't using it. So either that, I guess it was so bad I can't remember, but no. So anyway, when n gets large, okay, when n gets large, the sampling distribution, okay, so remember sampling distribution is different than sample distribution. The sampling distribution of the mean gets close to normal. Okay, it begins looking more and more and more and more like a normal distribution. And depending on what distribution you're starting with, I mean, you could be starting with a normal distribution, in which case then sample size of any size, the sampling distribution is normal. But even with our square, you know, our rectangular looking distribution with the numbers 1 through 9, as n got larger, you know, that had this definite peak in the middle. It looked like this thing we call a normal distribution. Okay, and a normal distribution would have a basic population shape like this. Okay, the bell-shaped curve, as many refer to it. And a standard normal distribution has a mean of 0, symmetric about 0. And in this curve, actually this curve, not a big deal. I have to think a little bit about getting the constants right. But everybody in here was supposed to, you know, have college algebra before they ever had the class like this or something similar. This curve can just be described as essentially as e to the negative x squared. Okay, I mean, you've seen stuff like that. E to the x, e to the negative x. You've seen stuff like that. This curve is basically just the function e to the negative x squared. Not a big deal. I mean, you know, nothing. It's just a curve. But you know, what if we think of this as the whole population? So 100% of everything lives between the x-axis and that curve. in that area. The area is 1 of this thing. And so if we want to know how likely it is to get particular x values out of this thing, we can do that by looking at area. Okay, and so for something like this, if I wanted to know how likely it was I could get, maybe this is the number negative 0.5, and this is the number negative 2. If I want to get the probability, so here's a member of my population, anything actually from -infinity to infinity. But if I want to know the likelihood or the probability that x is between negative 2 and negative 0.5, it's just equal to that area. Now that's true for any probability distribution. I could draw any curve, any shape I wanted, as long as the area underneath was 1. Then to talk about the population being here on the x-axis, how likely is each of those? That's the idea. That's why we have you read histograms. Okay, because this is basically a histogram with curvy tops instead of straight tops. How did you find the likelihood of some value here on a histogram? Well, you took the area of that frequency, or you took that relative frequency. So we're just taking bars of histograms and adding them up to get probabilities, and that's all that's happening. And so we can draw it though visually with just shading in areas of the curve. And what we know is that, relatively speaking, as far as these areas under the curve, every normal distribution looks like every other normal distribution. So this one, the standard normal, in some sense, it's the only one you ever need to know. Okay, but how much of it do you know? Not very much. I mean, you can memorize a table. Doesn't sound like fun to me, but we do along those lines, since they really are all the same as far as just this shape and getting areas. We do like to kind of keep track. We suggest, and this is just a typical thing we do in pretty much any statistics class that talks about the normal distribution. We do ask students to do one bit of memorization about the curve, and that is what we call these rules of thumb. And actually, I find them really helpful for just getting, back of the envelope kinds of things. Again, you're all taking this class. It's required of you. Some of you will take more statistics later in your life because of whatever career path you do, and you'll truly use things like the rules of thumb. Some of you, probably won't. But again, they come in handy, I think. If you look at things quantitatively at all, as far as things where they report standard deviations, that sort of thing, I really do. I think they come in handy to give you an idea of what's really going on. And these rules of thumb are based on standard deviations. And when you look at a standard normal, the standard deviation is 1. Okay, so, as you came out, if you came out here 1, 2, and so forth, each of those is one standard deviation of the population. And so we'll redraw it here. So there's 0. There's 1, 2, 3 standard deviations of the population, and I could come out to 4 and keep going. It goes to infinity. Minus 1, minus 2, minus 3, minus 4. Now, we'll see that I didn't really draw this very well if you really start thinking about scale and so forth as we look at this. But what we know is that if I know a population behaves like a normal distribution, and lots and lots and lots of populations do, now why? Actually, I think there's an intuitive reason for that is, again, theoretically, mathematically, we can show that means, right, sample means, generally from any distribution, doesn't matter what that distribution looked like, but if you get enough enough objects in your sample mean, enough observations in there, that distribution looks like a normal distribution. Well, when you think of things like height of a human being, an adult human being, what goes into that when you, well, it's the average of a whole bunch of things working together. A whole bunch of things, right? Including time goes into that. You know, your nutrition, your heredity, right? You know, all the genetics and all that stuff goes into your height. Well, when you think about that, then your height is sort of an average of a really large sample of stuff. Oh yeah, so it seems reasonable that our heights might be normally distributed. Weights normally distributed. Go to lots of living things, normally distributed. Go to lots of non-living things. You look at aspects of those, still normally distributed. Why? Again, intuitively, because all these things are made up of a huge number of little things that all came together as sort of an average. So it is very, very reasonable that a whole lot of things around us, if we think of their populations, they would look like this. They would have these characteristics or something really, really close to it. And so if we look at, you know, if we can look at a population and know its standard deviation, then, or a sample, you know, that kind of thing, then if it's normally distributed or pretty close, what we know is that inside plus or minus 1 standard deviation, 68% of the population is in there. Okay, so 0.68 in there. And it kind of doesn't matter what. Now, actually something I didn't mention, of course we have symmetry here. So I know, you know, here's the middle, the mode, it's also the mean. It's also the median, because everything's symmetric. I know that half the population is on that side of the average, half the population is on the other side of the average. So half the population is below average, half the population is above average. So that's actually something to think about, you know, is that, you know, when people start talking about average and above average and below average, well, actually, being below average isn't necessarily such a horrible thing. It depends on what you're below average at and your aspirations and all that. But 50% of the population, by definition, is below average. It's just the way it works, right? So, you know, you're pretty much, you could go with, well, I'm average height. Well, probably not really, because if you truly took the whole population and got average height, right? It would go out many, many decimal places and probably doesn't match you exactly. So everybody is either above average height or below average height, realistically. So, so that's 68% of the population, though, is in plus or minus 1 standard deviation. 95% is in between plus or minus 2 standard deviations. And then 99.7, so almost all of the population, 99.7% about, is between plus or minus 3 standard deviations. See, so if I know the mean, and I know the standard deviation, and I have any reason whatsoever to believe that the population we're talking about is somewhat normally distributed, I can kind of give you ideas of how things are, where this sits in the population. And an example of that in your text that they use is SAT scores. Now, anybody take the SAT that's in here? You did. Okay. You're like probably the only one. Yeah? Anybody else? Yeah, because hardly anybody in the, kind of in this region, in the central region of the U.S., takes the SAT comparatively. I don't want to pry. You don't have to answer. But did you consider some Eastern schools or West Coast schools or anything like that?
Yes, but our high school, considering like we're one of the top high schools in Indiana, we were required to take the ACT and the SAT.
Oh, they just required it of you. Oh, okay. Yeah. So, so some schools would do that. But also, many Eastern schools, East Coast schools and West Coast schools ask for the SAT as opposed to the ACT. And so, some people will take that. But what I'll do, so the book talks about the SAT. I'm going to talk about the ACT. And what we know about the ACT is that the mean is approximately about a score of 21. Right in there somewhere. So we'll call it 21. What's the top score on an ACT? 36. Okay? And if one gets a 36, your report will say something like you're 99th percentile. Right? You scored better than, I shouldn't say you are better than, because it's just a score. You scored better than 99% of the population. Well, where the heck did they get that? Well, actually, the standard deviation is about 5. And so, if I were to draw a normal distribution, and the scores are normally distributed, then what we would have is, there's 21, there's 26, 31, 36, and actually this holds for both the composite or any individual score. 16, 11, and 6. Now, I have a friend who maintains he got a 3 on something. I think he's lying, because I think...
that much for writing your name.
But I think it's very likely that the lowest you can get is a 6. I haven't looked at it in a long time, so I don't really remember. But who knows? It could be that you can get below a 6. Any rate, so as we look at this, you can determine sort of your percentile based on these rules of thumb. And so what we know is pretty much nobody is down here. But then, if we kind of think about trying to fill in here, remember this is 0.68, but I also know, this is symmetric. So that's actually 0.34, and that's 0.34. Then 95%, well, there's 68%, so I've got another 17%, or 27% in here. But it's split. So there's 0.135 and 0.135. So about 13.5% of the population is in there, and 13.5% of the population is in there. And then we go another 4.7%. Okay, so that'd be 2.35% in each half. And so that's 0.0235 and 0.0235. And then we've got that 0.3% left. So that's 0.15%. So out here we have 0.0015, and out here we have 0.0015. So if I start from the left and start adding things up, then if I get to a score of 11, then that means I have the 0.0015 and 0.0235, so about 0.025, or the 2.5% percentile. Then I add another 13.5% to get a 16, and so 13.5 would be 16% here, 0.16. Okay, so 16th percentile. Then I add the 34. If I got a 21, I'm at the 50th percentile, 0.50. If I got a 26, I'm at the 84th percentile because I add that 34%. If I got a 31, I need to add that 13.5%. And so what is that, 97.5? So 0.975. And then finally here, they'll call it the 99th percentile. And it might be, again, these are all approximate, but it would be 99.85 percentile, so 0.9985 as we look this way for the population. Okay, so somebody tells me their ACT score, I've got an idea of kind of where they sat compared to the rest of the population. On the whole, you probably don't care. I don't know, maybe you go to parties and compare ACT scores. I don't remember doing that when I was your age, but when I'm thinking about placing students or talking to students about courses and that sort of thing, it's kind of nice to have a feel for that. And so that is a place where we have a normal distribution, and you can get a pretty quick rule of thumb from something, So, somebody who's got a 31 on their ACT, they did pretty darn well, right? But actually, a 26, pretty darn good too. I mean, it didn't fall off that much compared to sort of the progression of the scores, right? I mean, you're still doing, at a 26, I mean, you're still 84th percentile. I mean, I think that's good. You know, and as far as that score. I don't want to make too much of the ACT itself. It's just that it's normally distributed, and that's what we're talking about. And so that's a rule of thumb that I can use personally when I see scores. And again, it means I don't have to keep looking something up in a chart all the time because, oh, I know the rule of thumb. I'm good enough with the numbers that I can come up with these pretty fast, much faster than even trying to look things up. And you know, and so when if somebody has a 24 or a 28 or something like that, oh yeah, I know there's somewhere in the middle there between those things. Okay, so that's this rule of thumb idea. Is what you can do is if you turn things into standard deviations, then the only distribution you ever need is the standard normal distribution. Well, I mean, as far as normal distributions. Okay? And so your textbook talks about this thing, the z-score. And all that is, a z-score is the number of standard deviations. That's a number sign. It's also a pound sign. It's also a hashtag, right? You know, but it's the number sign. So z-score is number of standard deviations. But I don't know, maybe Twitter has a hashtag of standard deviations. I have no idea. I doubt it. Maybe hashtag standard deviations. I doubt the of part. Right? So that's all a z-score is doing. Right? So if I'm told that, you know, maybe I take a sample, and from that sample, I take the sample mean, and, you know, I get a 48, and then I find the sample standard deviation, and maybe that's a 4, something like that. And then, you know, I could ask, well, if that's what I think is going on with the population, then I could ask, well, what's the likelihood or probability? Okay, probability of being between 40 and 56. Well, what they tell us to do in the textbook, and I happen to pick the 40 and 56 just because it will give me a number I can do without looking it up, or get pretty close to it anyway. So, you know, the way I might write this is I want the probability that 40 is less than X. Well, what's X? Well, someone from my population or some theme from my population. Less than 56. Well, I don't know. I have no idea. But what I can do is, well, actually, I do have an idea because I picked the numbers. But what I can do is create z-values. And my z-value is just my number that I want, so my x, minus my x bar divided by, oops, not sigma, s, or sigma, if I know the population standard deviation, but I usually don't. And so each of these numbers I can do that with, so I could do a z1, which is 40 minus 48 divided by 4. Now you see what it's doing. I take the 40 minus 48, that tells me how far I'm away from the mean. Right? It tells me the distance from the mean. I'm negative 8 from the mean. Right? I'm 8 units to the left of the mean. Oh, but how many standard deviations is that? Well, each standard deviation is 4 units. So we'll divide by 4. Oh, I'm 2 standard deviations. Well, actually, minus 2 standard deviations away. So that's minus 2. And then I'll call this Z2. And that's my 56 minus 48 over 4. And that's a plus 2. And so when I turn it into standard deviations, then, at least up to how well I know the Z table or the standard normal table, I can tell you the answer. Because my probability of 40 being less than X being less than 56 is exactly equal to the probability that negative 2 is less than Z, and we always use a Z for the standard normal, is less than 2. But I know that is about 95%, because it's standard deviations. And I can check that. Okay? So I think I have Desmos up. I'll have to pull up a spreadsheet as well, but no, I might not have Desmos up. Okay, so let's open that. Go find Desmos. Okay, in Desmos, actually, now you can get a little fancier with things and so forth, but if I just type in normal dist like that, all of a sudden the type changes. It goes from being slanted, looking mathy, function-esque-ish to very normal formal type. If I just do that, let me make this projector mode and maybe a little bigger. Now it also plots it over there, but there's the normal distribution, and down like that. And it says the mean is 0, the standard deviation is 1. Well, if I want to change that, I can, but for the moment, I'm going to leave it as 0, 1, the standard normal, and I'm going to determine that probability, and all I have to do is click that cumulative probability, and the minimum, I'll make negative 2, and the maximum, I'll make 2, 0.9544. That's why we say the rule of thumb is 95%. So actual 95%, not 2 and minus 2, it's 1.96 and minus 1.96. Okay, 2 and minus 2, pretty close. And so I got it that way. Now, though, I could change that normal distribution in there to have a mean of 48 and a standard deviation of 4. And so all I have to do is go in here and type 48. That changes the mean. And then comma and 4. That changes the standard deviation. And now I wanted to know between 40 and 56. And there's the 0.95449 again. So Desmos, I can get this normal distribution very easily. We have a table in our book that we can look it up there. I'll probably do videos on that. Or I have, well, actually, I think I have videos on that. I don't know. You all can correct me if I'm wrong. I'll look to make sure. I know I've done videos on that. I'm pretty sure they should be posted there. But just to make sure, I'll go back and look. But yeah, so with decimals though, I can get that normal distribution, just dandy. And I can do the same thing in Excel. Now I will say for something like this, I think decimals is by far the easiest. And what's interesting is it's that same command in a spreadsheet. So, you know, if I open a spreadsheet and there it is, make that a little bigger. Now the problem with the spreadsheet is all it knows how to do is the same thing that your book knows how to do, and it only knows how to find the proportion of the population from some x value or z value all the way to minus infinity. It's the only way it knows how to do it. And so, if I want that, if I want, I got to go back here though. See, so if I'm going to record these, I have to be able to remember to show people, you know, what I'm doing. So if I want, let's just erase this, make this a little bigger. So in both Excel or usually looking up in a table or something like that, if I want some middle area like this, you know, how much of the population does that represent? How much is in between those two values? Some x1 and some x2. What I have to do in both Excel and in using a table in a book or on the internet or something like that is I can only get the area from some number all the way left. And so what I have to do, ooh, that was pretty bad, okay. I have to take that area all the way to the left minus that area, there's x1, I have to take that area minus that area. And so, you know, if I do something like that in Excel, I can do equals, and again, it's actually it's not normal dist, it's norm dist, I think. Yep, norm dist. And then the number, okay, so we had 56, comma, the mean, that was 48, the standard deviation, that was 4, and then, yeah, on the newer versions, actually I'm going to try this without putting the 1 in there, but it says comma C when I'm looking at the directions, and that C is just to tell it, yeah, find that area to the left. If you put a 1, that's what it does. If you put a 0, it gives you the height of the curve there. You don't want that. Okay, I mean, so you want to put a 1, but I'm going to try it without the 1 and just see if I get an error. Yeah, see, I have an older version, so see, it doesn't give me an error. Some of you are getting errors. So I'll go back and put the 1 in. And I get the 0.977, and then I do the same thing, equals norm dist, and this time I want to use 40, but it's still the same mean of 48, still a standard deviation of 4, still use a 1, and I get those two numbers for my two areas, and I have to subtract the top one, or well, actually take the top one and subtract the bottom one. And there's that same 0.95497 thing. So same answer, okay? And you could do it with the negative 2's and 2's with a mean of 0 and 1. So we have various ways. There's the table in the text. There is, Excel here, and there's this normal distribution. Now, if you ever do want to, on something like Desmos, if you want to get that area to the left, all you have to do in here, I think you've got two options. One, you could start typing infinity, I-N-F-I-N-I-T-Y, and all of a sudden it changes to infinity, except you need a minus infinity. I didn't put the minus in front of it. So I can do an arrow over here and minus, and you see you get the 9772, just like we did in Excel. So you can type it that way. I think, actually, if you type small o, I'm going to try that. Didn't work. Okay, I think at one time that worked. Let me try a large O. Nope. I don't know, that doesn't work anymore. Maybe it never did. Maybe I'm just fooling myself. But I thought it did at one time. You could just type two O's, small O's, and it would go, oh, that's an infinity sign. Not anymore, I guess. Infinity. So we get our minus infinity. You could do the same thing for the right-hand side. Now, what's nice with the Desmos is I can get a right-hand side one if I just want to know how much area is to the right of a number, because I could just, I could do something like go from the 40 all the way up to infinity just by typing in, again, infinity. And again, the symmetry, if I go from 40 up, that's the same thing as starting at the left and going up to 56, because they're both two standard deviations away from the mean, one to the left, one to the right. Okay. Let's see. So, we use this normal distribution. I'd like to point out that I did, and I have to, I guess, apologize. These only went up a couple of days ago, but they've been ready for a while. I guess I just thought I had them up. Oh, wait, wrong place. Go back here. Well, maybe. There we go. Quiz stuff. Quiz resources. So there are 3 interactive practice things. Confidence intervals, we haven't talked about that live, but there's confidence intervals, some practice for the quiz for that, working with normal probabilities in the z-table, some practice with that. And of course you can always use Desmos or Excel or whatever to do the calculations. And then the rule of thumb things with the standard deviations. So there's some practice with those that you can try. And I'll keep working on anything that I can add. And if you have any questions, feel free to send them to me. Ask me any questions you want. And I guess that's it for today. I'll see you on Thursday.